So today we're going to talk about something different, right? We saw the preliminaries of Lotka-Volterra, then we talked about Lotka-Volterra with random parameters. Today we're going to do something close in the sense that we're going to look at models for metapopulation dynamics with random parameters. And then in the middle, we had a foray into the real world with actual data. And now we're back to theory land. Okay. And I'm very happy that this get me to say a few words about Richard Levis, who is one of my favorite scientists who passed like a few years back. And he was born in Brooklyn and then studied mathematics and agriculture, and then embarked in this career that it was between science, political science, philosophy, mathematics, and Marxist revolution too. He moved to Puerto Rico when he was blacklisted as a communist this was during the Korean War, and with his wife and set up a farm, but then went to the University of Havana. Even before he got his PhD, he was organizing like the Department of Biology in Havana. And then in 1967, he moved to the University of Chicago with Richard Levontin. And so this picture, for example, is from the U Chicago archive. And there are other pictures of Richard Levis at anti-war rallies against like the Vietnam War, also at the University of Chicago. And in fact, I am at the University of Chicago because of Richard Levis, not because he encouraged me to go to the University of Chicago or anything. But when I was applying for a job, I had been in the US for 3 years, I think, at that point, and I knew nothing about the American university system. So I didn't know that the University of Chicago was a great university. But they said, oh, but I remember reading papers from Richard Levis from the University of Chicago, so if it's good for him, it's good for me. And so I applied, and here I am. And he made like incredible contribution to ecology, and really, really clean thinker. And I would just like to remind people of like the idea of evolution in a changing environment. This was work done in 1968, 1969, which I think it's still very fresh, and it's still a problem that we were discussing even during these lectures, like in these days, of how do we track for a changing environment. And then the idea of limiting similarity, he worked with MacArthur, which we've seen before, and then he developed this idea of metapopulations, which is what we're going to talk about today. And my favorite thing, like loop analysis, which is like the qualitative analysis of differential equations, which I did for my undergraduate thesis. So that's how I encountered his work. Okay. But today we're going to talk about metapopulations, a term that Richard Levis coined in 1969 when he was a professor at the University of Chicago. And the idea is a population of populations in which there's two processes. One is local extinctions, right? So a population locally can go extinct, but then other populations can send propagules, right? Can send individuals to this place and recolonize it. So there's this balance between colonization or immigration and extinction. And the picture that he had in mind is, imagine that you have a landscape, and in this landscape there are patches of suitable habitat, right? So this is a meadow where a certain butterfly can live, and then here is another meadow, etc., and it's a fragmented landscape of some kind, right? And each one of these patches can be in one of two states, right? It could be occupied by the butterfly that we're interested in, or it could be absent, okay? And then there are these two processes. This patch can go from being occupied to go empty, right? Can vacate the patch because of a local extinction, right? So like the butterfly disappears from this. And then patches that are occupied can send propagules and colonize an empty patch. Okay, so there's only these two processes. And now Levis made like the assumption in which we have fundamentally infinitely many patches, or a very large number of patches, and all patches are connected with each other, right? So what this means biologically is that the distance between this meadow and this meadow, it's not a long distance if you're a butterfly, right? Like it's within reason, right, to move from here to there with the same rate. Okay, so if you take these two assumptions, then instead of maybe tracking the number of patches that are occupied at any point in time, we might want to just track the proportion of occupied patches, which we're going to call P of t, right? I use just P just to say this is a proportion. It's a number between 0 and 1, right? Or a probability if you prefer. And then we could say that we have the empty patches that we can call Q of t, which is going to be at this point 1 minus P of t, right? Because they have to sum to 1. Okay, and then we have two processes. We're going to use a gamma is the colonization rate. And then I think I use in the notes delta for extinction or mortality. Okay, so then we have two equations. Okay, the first one describes the dynamics of the occupied patches. So the occupied patches, P of t, well, let me remove the t. You know that P changes in time. There's like the mortality, right? So occupied patches become empty at rate delta. And then we have that at rate gamma, we have that the occupied patches produce propagules, and these propagules can encounter the empty patches, right? Q. Okay, so this is the basic dynamics. And then we can write the equation for Q, but what is it going to be? Right, it's going to be negative of P dot, because if there is a constant that is maintained by the dynamics, in this case, the sum like of P and Q is 1, then the sum of the ODEs must sum to 0, right? We're working in a simplex. So this would be delta P minus gamma PQ. Okay? And because of this, right, because we have a conservation of one thing, then we can basically write these two equations as a single equation, right? So we could say I write Q as 1 minus P here, and then I remove Q altogether. So this becomes an equation that depends only on P, or you could do the same here and have an equation that depends only on Q. So we're going to do the former. P plus gamma P times 1 minus P. Okay, which is equal to what? Like we can take P out, and then we have a gamma minus delta minus gamma P, which is the equation of what? It's an equation that you saw day one, the logistic growth, right? Where this is my growth rate, and this is going to be a term that determines self-limitation. So we know everything about this, right? If this growth rate is positive and this gamma is positive by definition, then dynamics will converge to an equilibrium that is globally stable. Okay? So this was a very simple model that then turns out to be fully explained by whatever we know about the logistic growth. Just out of interest, right? There are other models that look exactly like this in another area that is connected with the ecology and evolutionary biology, which would be the ecology of infectious diseases, right? If I take these, instead of being patches, we call them people, right? And we call colonization infection, and extinction, we call it recovery. What do we get? We get the so-called SIS model, right? In which we have a population, we divide it into those that are susceptible to a disease and those that are infected and infectious for a disease. And when they recover, they go back to being susceptible again. So it doesn't provide lasting immunity. What you would get is exactly the same equations that we have, right? So like we have three different ways to get to the logistic growth using different areas of biology. Okay, so this was 1969, and this idea of a metapopulation, so these kind of populations connected by immigration from one patch to the other, became very, very popular, and there's infinitely many papers that propose variations on this theme. For example, there are papers that look at what if, instead of assuming that butterflies can go from anywhere to anywhere else, we have an actual network of dispersion, such that traversing a long stretch or going through some barriers, it's more difficult than just like going to your neighbor, right? And so if you look at the work of Hansky and of Askainen, you find a lot of these modeling of metapopulations on network. Another very interesting and very difficult problem is what happens if instead of tracking only one species at a time, we track like a community. So imagine that we have predators and prey, and each patch could be occupied by the prey or the predator, but the predator by itself would die, or the predator and prey, in which case they could persist, and they can disperse at different rates, maybe using different networks, right? So this would be a more complicated model. And then just to mention the work of my student, Zach Miller, that then we were going to see for another paper on metapopulations. One problem that we tackled recently that I think is very interesting, especially in the context of diseases, is what happens when you occupy a patch, you change it, right? Imagine that you're a beaver, right? You go in a place and you build a dam. Even when the beaver goes locally extinct, the dam is still there, right? And so it has changed the environment for good. And when we're talking about viruses, for example, every time you catch a virus, you mount some sort of response that then gives you some either lasting or waning immunity. And so you have changed the patch, in this case, the person, for the next virus to come about, right? And so that gives rise to very interesting dynamics. But today I would like to talk about another such extension of the model that deals with the case of many species, so it's more ideologically aligned with what I've been presenting this week. And these species live in some sort of trade-off space, right? So species could either be very good at colonizing, so imagine things that can produce very many, seeds, or disperse them very far, very quickly, or they could be good competitors, right? Once they occupy a patch, it's very difficult to kick them out of this patch, right? So imagine that now patches can be occupied only by one species at a time. And this is what happens, for example, if you have, a mussel bed, right? Like if you have a mussel bed, there's space for so many mussels, and there's maybe different species of mussel competing for this, but it's somewhat of a zero-sum game, right? Like there's only so many slots that you can take. Or a tropical rainforest, right? If you look at the picture of a tropical rainforest from above, there's basically no space in the canopy, right? So the only way to get a new tree is to kill another tree. And so we have these zero-sum dynamics. And so what we're going to have is a model in which you are assigned some sort of competitive ability and a colonization rate. And then you can imagine that this trade-off is the only way to have species coexisting. Because if I am a better competitor and a better colonizer than you are, I'm gonna send you to extinction, right? So if you go back to the first studies of these metapopulation models with competition colonization trade-off, right? They were arguing for the fact that this is the only way to have many species coexisting. All right, so because we have many species, the notation is slightly more complicated, and then we're going to see that we can massage this into our usual friend, the Lotka-Volterra model. So it looks complicated, but it's the same that we've done before. And so what we're going to say is like PI, right, is the proportion of patches that are occupied by species I, okay? And then, therefore, we have that if I sum for j equals to 1 to n pj, this has to be lower or equal than 1, right? Because we're not tracking q, the empty space, as much as we did before, right? So we're already in the space where we just take it implicitly. Okay, and these species can die at a certain mortality rate, mi, according to how many patches are occupied by pi. Okay, so this is exactly the same as we had in the other mode. Then here it starts diverging, right? So we're taking this sum, but we want to see for j equal to 1 to I minus 1, right? Where I'm saying if j is equal to 1, this you don't have a sum of cj pi pj. So what does this mean? If you think about it, so what we're going to say is that Ci is colonization rate for species I. And I'm going to say that if Ci is lower than Cj, right? So if you have a worse colonization rate, then Ci is superior competitor. Okay, what does it mean in practice? That to any species that has a colonization rate lower than you have, your patch that you're occupying looks empty to them, right? So they can come and kick you out of the patch. Okay, so these are the sum of all the J's that are superior competitors, and they will send propagule to your patch and kick you out, right? That's why there's a negative sign here. Does this make sense? Okay. And then we want these equations so far, you can only die, right? Because there's only negative numbers. So we need to have a positive contribution. This positive contribution is going to be with your colonization rate, your patches can send propagules, and they can send them where? In patches that are either empty or they are occupied by inferior competitors. Okay? So instead of writing like the sum for J is equal to I plus 1 to N plus the empty patches, because we know that the whole thing, like the empty patches plus all the occupied patches must sum to 1, we're going to write this as 1 minus the sum over J that goes between 1 and I, right? So all those that have better or equal competitive abilities, PJ, sorry. Okay, so these are the superior competitor, kick you out. And here is you kick out, these are the proportion occupied by inferior competitors. Okay, does this build up of the equation make sense to you? So as I said, it's a little more involved. But these are the three processes. From J that goes between 1 and I. Sorry that I erased it. I'm left-handed, so I tried to write and erase at the same time. Okay, so these would be all the patches that are occupied by superior competitor to you, or in the case of I, by yourself. Okay, so all these patches are non-empty to you, and so 1 minus those are those that are empty to you.
But does it assume some sort of a rank ordering of the competition rates? Like, is there some ordering and indexing?
Yes, that's what we're saying here, right? That we're looking at the numbers, and now, oh yeah, that's a very good point, right? So we want to order the species such that C1 is lower or equal than C2, lower or equal than Cn. Very good point. Yeah, I am assuming always that I already sorted them in order. Thank you for reminding me. I forgot to add it to the notes. It's these things that you forget because you've seen this thing too many times.
The statement better colonizers being worse competitors. So they colonize the patch, but then they have to be more competitive than the species already existing, right?
So those that are good colonizers, they basically send their propagules. Imagine like the one with the highest colonization rate can colonize only empty spaces, right? But does so at a very fast rate. So as soon as somebody dies and leaves a patch empty, this guy comes about and stays there. Then what happens? That somebody else comes about and kicks you out, right? So you have to be able to reproduce and send propagules to some other empty patches that became like available right now before they can kick you out, right? That's the way these last species will survive. While the first species, they will go maybe very slowly, but every time they look at the patch, they look at the patch that it's empty to them, right? Because if there's somebody, they can kick them out. And if it's empty, it's empty.
But I can't understand the intuition behind why better colonizers are worse competitors.
Okay, so it's inspired by some sort of life history theory of like grassland, right? So that you can have different strategies. You can either reproduce very fast and try to get into these kind of marginal environments before anybody else, or you can grow like very robust and nobody can kick you out, right? So this was the inspiration. But you imagine that in a model of this kind, if I had somebody who was both a better colonizer and a better competitor of everybody else, then what would happen? We would have only one species, right? So this is the only thing that it's interesting to study. It's where there is at least partially some sort of trade-off, because otherwise we already know the answer. It's going to be only one species and it's exactly like the Levin's model of 1969.
So where is this fact embedded in the equation?
In the ordering here, right? So we order all the species from the one with the lowest colonization rate to the highest. And so when I'm summing from 1 to I-1, I'm summing only over your superior competitors that have lower colonization rates. Yeah, this was the question there that I forgot to make.
Yeah, I haven't quite got it. You are summing over those species
that have lower colonization rate than you do, fundamentally.
That have lower colonization rate.
And therefore are superior competitors. So that when they come about, they can kick you out.
Yes, so this is fine. That's fine. And the other one is just whatever you can colonize, right?
This is 1 minus all the patches that are occupied either by better competitors than you are or yourself. So these are all the ones that are worse competitors than you are. 1 minus that, or empty.
Yes, these are either empty or colonized by those who are inferior competitors.
Perfect.
But this fact that better colonizers are worse competitors, where is that embedded in this structure?
Just in the sums. That the sums only run from 1 to I, and these are ordered.
But that's simply the statement that in this there is an ascending order of competitiveness. Where does the colonizer part come in, right?
Okay, I think that if we do the next section, which is turn this model to GLV, then you will agree with me, and it will be obvious what's going on. Okay, so let's try to do that for a second, and then we can see whether this solves the conundrum. Because I agree with you that the first time you see this model, it's a little puzzling. So how do I recognize that this model is in fact our friend the Lotka-Volterra model? Well, for one thing, you can take pi out, right? That's for sure. And then here, what do I have? I have a negative of mi. And then I keep the sum the same, minus the sum over j. That goes between 1 and I-1 of Cj Pj, which would be some sort of Lotka-Volterra looking thing. And then here I expand. I get a Ci from here. And then Ci sum over j equals to 1 to I of Pj. I'm going to write it as the sum that runs only to I-1 plus one element that is Ci. Right, so I'm going to write this as minus Ci Pi minus the sum over j that goes between 1 and now I-1 again, right? So here we had I, but I took the one with I out, and now I have I-1 of Ci Pj. Okay, now it's looking a little better. Now what I'm going to do is to say this is a Pi. And then here I have Ci minus Mi. That should remind you of Levy's model, colonization minus extinction, right? This is exactly the term. This is the equivalent to the growth rate of the population, the intrinsic growth rate. And then minus Ci Pi. And then minus the sum over j is equal to 1 to I-1 of Ci plus Cj, Pj. Okay? Now if I call these things Ri, right, the growth rate of population I, and then I put all these coefficients into a matrix, sum over j of Aij xj, Pj, sorry, force of habit, then I get my Lotka-Volterra model. Okay, now what we haven't said is how does this matrix Aij look like? And you can see that it has Ci on the diagonal for sure. And then it has Ci plus Cj only when we're in the lower triangular part of the matrix, and otherwise it has 0. So A would look like C1, C2, C3, etc. Here I have only zeros. And then in here, I have CI, like the row index, plus CJ, the column index. Okay, so you can see that this is a highly hierarchical Lotka-Volterra model. So it's very different from the Lotka-Volterra model we've seen before, where we had completely unstructured systems. Here, there is a strict hierarchy such that the first species interact only with itself. The second species only interact with itself and the first species. Right? The third species only with itself, the first species and the second species, and so forth and so on. Okay, so very hierarchically structured. Does this help visualizing what the model is doing? Yeah, go ahead.
What will happen if both species have same competitiveness? Like if CI and CJ is
yeah, then they're fundamentally the same species in this model. You can sum them.
Achha, so they won't be distinct.
Yeah, you could distinguish them if they are different mortalities. If they are different, same mortality, same colonization rate, then to us they're the same species.
So what is colonizing versus competitive? I mean, what are these two axes? That's not very clear to me.
Biologically or in the model?
Both biologically and in the model.
So colonizing, like a fast colonizer, means I have a very fast generation time. I can produce, for example, if I'm a plant, these models were born in the space of like plants, right? So imagine that I have a grass that can come in as soon as a tree falls, like in the forest, there's a patch that it's empty, like grass can come here and grow, reproduce, make their seeds very fast, and then send them like somewhere else, right? That would be a very fast colonizer. But there is no way grass can kick out a tree of a patch, right? While a tree can shade like lower shrubs and kill them, right? By shading. So like a tree in this ideology would be looking something like with low colonization rate, right? Because it takes a very long time for growing the tree, making the seeds, and eventually dispersing. But it's very difficult to move away from this patch once you have it, right? Like because you cannot shade it or you cannot kill it in very easy way. Does this make sense biologically?
Yes, it makes sense biologically.
So it's like if you think about like all theories of R versus K, like these kind of ideas, right? That's like the ideology behind this type of models.
Yes, but what I don't see clearly is how this feature is embedded in the model.
So you agree with me that imagine like for simplicity, we take M to be the same for all the patches, which we're going to do later.
Fine.
Then you can see that the growth rate increases with the colonization rate. Right, so the larger this number CI, the larger your growth rate. Okay, so that's like the one part. The other part is this matrix is upper triangular or lower triangular. Mm-hmm. So there's this hierarchy of competition.
Yes. So the larger the CI, the higher is your growth rate.
But then at the same time, you suffer from the competition of many more species.
Okay, got it. Yeah.
Fantastic. Okay, so we did step one, which is we went from something that looked a little iffy, right? That was a bit difficult to parse, to something that we've seen already for the whole week. And in fact, you cannot take this anymore, but this is the last lecture, so you're fine. Okay, and what do you think I'm going to do next? Like another feature that we've seen in many of these models of Lotka-Volterra was to say, well, can I have this condition that guarantees that every feasible state would be stable, right? Because then I can do dynamics very easily. And sure enough, this model is exactly of that kind. So I want to spend maybe a little time doing this because like we have proof in the paper that you find in the references, but I think it's a bit like too, not snob, but like it's a bit like too high mathematics. So I wanted to come up with a different proof that it's like more intelligible, I believe, even though it's a little more laborious. But just to show you that when you have an interaction matrix of this kind, then you can always find this condition for global stability. And if you remember, like what we were saying is that if we have a matrix A such that we can find a positive W with WA, D of WA, diagonal of WA, plus A transpose, diagonal of W, In this case, because we have a minus interaction sign, it has to be positive definite, meaning this is a symmetric matrix and all its eigenvalues are positive. Then we have these Lyapunov functions for Lotka-Volterra that we've seen over and over again. Okay, so how do we go about showing that there exists a W for any generic system, right? Like what we're saying is only that the only thing that we know is all these numbers are positive, and then we know that C2 is larger than C1, and C3 is larger than C2, etc., etc. Okay? So you think about it for a while, and then you can say, well, you know what I'm going to choose for W? I'm going to choose the reciprocal of the colonization rate. Right? So I'm saying Wi is 1 over Ci. And this is definitely a positive number, so it abides by the rule that we want, right? And so this matrix is the sum of this matrix and its transpose. So let's look at what is D of WA, right? So we're saying D of W times A is equal to the diagonal of C inverse A. And how is it going to look? So what does this operation do to this matrix? It takes each row and divide each rows by the corresponding Ci, okay? So on the first element, we would get 1, and then 0, 0, 0, 0, etc. But there's a question? No. What would we get in the second element? So we would be dividing this number by C2, right? So we get 1 on the diagonal, and here we have a C2 divided by C2, which we can write as 1, plus C1 over C2, and then 0, 0, 0. So far, so good? Okay. Then let's look at the third row, right? We would still get 1 on the diagonal. And then what would you get? There's going to be a C3 in all of these numbers, right? But then we're going to have 1 plus C1 over C3, and then 1 plus C2 over C3. Okay, so this is the way this matrix is going to work. 1 on the diagonal, 0 on the upper triangular, and then here we're always going to have 1 plus Ci over Cj. Okay, so now we can see that at least it has a simple enough diagram. Now, if we take this and sum its transpose, what we're going to get is just 2 on the diagonal, right? So maybe I should cancel something or not. Maybe I can do it here. So we want to do D of W, A plus A transpose D of W. We'll have 2 on the diagonal, okay, across the whole diagonal because we're summing one with itself. And then here we're going to sum 0, so this will remain 1 plus Ci over Cj. Right? But then here, because we're transposing, 1 plus Cj over Ci. Okay, so this would be the structure of this matrix. Now, when we say positive definite, what do we really mean, right? One way to say positive definite is to think, oh, the eigenvalues are all positive, right? And they're real. Another way to think about positive definite is saying, for every, if let's say that the matrix, I don't know, H is positive definite, then I can take any vector in Rn that I want, that it's not 0. So X is not belongs to Rn, and X is not 0. And then I can compose this quadratic form, and this is going to be greater than 0. Okay, so this would be a positive definite matrix, and this would be a positive semi-definite matrix, meaning there are some directions that sum exactly to 0. Okay, so with this definition in mind, the sum of two positive definite matrices is what? Is positive definite, right? Because I can take the sum over the first, and that's positive, the sum over the second, that is positive. The sum of two positive semi-definite matrices is positive semi-definite or even positive definite, depending on the exact thing, right? And so if you look at this matrix, you can see that you already have a positive semi-definite matrix is lurking, which is what? I have 1 everywhere, right? So I can write this Let's call this, I think it's called M in the notes. So you can write M as 1 transpose, so a matrix of all ones, right? Plus whatever remains, right? Now I have 1 on the diagonal, and then I have just Cj over Ci here, and Ci over Cj there. Okay, where this one, we know it's positive semi-definite. It has one eigenvalue that it's exactly n, and all the other eigenvalues are 0. Okay, so if I sum these, right, I get some, what is this thing? X transpose 1 transpose X. What is this quantity? In component form, right? This would be, X transpose 1 would be the sum of Xi, right? This one would be the sum of Xi. So it's the sum of Xi squared, which you can see it's positive semi-definite. Okay. Now, this tells you, if I have something of this form, right, where I have a transpose of another vector or matrix, I get a positive definite form. You can think about this and say, well, if I have a matrix, let's say A, that I can write as the outer product of two matrices, either B transposed or B transpose B, where these matrices are real numbers, then the matrix is positive definite, right? Because you can always do this trick of saying, imagine that I have X transpose AX, right? I can always write this as X transposed Q lambda Q inverse X. And if this matrix is symmetric, you can do the eigendecomposition in this way, okay? So if I have a symmetric matrix, I can always write its eigendecomposition, call this Y, call this Y, right? So we have Y transposed a diagonal matrix Y. So this is the sum of squares. And if these numbers are positive, then we have positive definite, okay? So what we're going to do to show that this matrix now is positive semi-definite is we're going to write it as the outer product of two matrices that are all real, and in fact they all have are non-negative coefficients. And this requires a little bit of staring at this thing for a long time, but if I define the matrix R such that Rij, that's right, just Rij is equal to the square root of Ci squared minus Cj squared. And you know that I is always larger than J, right, in this thing, because we're going this direction. Then this number is actually a real number, right? Divided by Cj if J is greater or equal than I, and then it's 0 otherwise, right? If J is lower than I, right? So if you build this matrix R, then this matrix here is R transpose R. Okay, and this matrix contains either zeros or positive numbers. Let me show you an example on the board for a 3 by 3, on the computer for a 3 by 3 matrix, so that I don't have to do all the calculations myself. So imagine that these are a generic matrix for 3 species, right? We have it here, A. Then we do this transformation. We take the ones out. We remain with this Q. And this would be the form of my matrix R. And then if you take R transpose R, you get Q. So then this is also a positive semi-definite matrix. Yeah. Sorry? J less or equal than I? Oh, yes. Sorry. J less or equal than I. Sorry. Yeah, you can find the right. I always get confused with these indices. Okay, so that's one way to show that this model not only is Lotka-Volterra, but it's Lotka-Volterra of the kind that I prefer, because then I don't have to think about what's going to happen to the dynamics, right? Having done this calculation, you can see that the dynamics of these models are going to be boring, right? whenever we have any initial condition, these systems will be driven to a saturated equilibrium, and it's always going to be an equilibrium. We will never observe interesting dynamics in this mode. And this is similar to what we were saying for generic competition models, right? But this is a very structured system. Okay? Fantastic. So the next thing that I would like to do is to discuss the equilibria of this system. So if you think about the equilibria of Lotka-Volterra, and for the people that were at the tutorial that Abby ran, right, she was saying one of the main computational hurdle of studying systems with many, many species is that we have to find equilibria. And first, there's 2 to the n that are possible, right? So there's a large number when n is large. And second, computing each equilibrium requires inverting a matrix. And inverting a matrix is computationally very, very expensive. And that's why, for example, we introduced this idea of like doing some sort of rank 1 approximation of the off-diagonal terms, et cetera, et cetera. Because in this case, we have a model that is very structured, we can find the equilibria of the system very, very fast. In fact, in linear time, right? So we can do these simulations without doing the simulations for tens of thousands, hundreds of thousands, millions of species in a regular, on your laptop, right? Without the need to use quantum computers. And so I wanted to show you how would you do this, and also that this gives you a very simple rule and a very simple intuitive way to think about who's going to survive and who's going to go extinct in this system. Let me just clear the board because then I have to draw a few of these things. So one useful graph that we can have is like the real line. And then we can place our value of m. And then look at the first species that would be the one with the smallest possible colonization rate. Right, so we have a 0 here, and we're assuming that this is my axis for like the colonization rate. And at some point, we have m. So for simplicity, from now on, instead of having a specific mortality for each species, I'm going to take the same mortality for all species, because then it's easier to do. Okay, then we can write the equation for the first species, which is P1. And if you remember, it's going to be P1 times, at this point, C1 minus M, because I put the same to all of them, minus C1 P1. Right, so the first species follows what? The Levin's model. The first species is exactly doing the Levin's dynamics, so it will, as long as Ci is greater than M, so if my Ci is here, C1 is here, it's greater than M, this will go to an equilibrium that is globally stable. And it doesn't care about any of the other n-1 species. Okay, so what we need for P1 star to be greater than 0, we need this C1 minus M to be greater than 0. And you can write this as C1. Well, I don't want to get ahead of myself. Let's write first the equilibrium itself, because then it's that's how I do it in the notes. So if I want to solve this equation, right, I write C1 P1 is equal to C1 minus M. So P1 is equal to C1 minus M over C1, which is equal to 1 minus M over C1. Okay, so this is my equilibrium if this thing is greater than 0. Okay, so as long as C1 is greater than M, we will reach some equilibrium. And depending if this is much, much larger than M, so we move here, this piece will occupy a large fraction of the landscape. And if this number is very, very close to C1, it will occupy a smaller fraction. So far, it's exactly the same as before. All right, and our condition here is C1 is greater than M. Okay, So now, what about the second species? So for the second species, we would have P2 dot is P2, and then we have C2 minus M here, minus C1 plus C2 P1 minus C2 P2. Okay, so now what we're going to do is to say, assume that the first species exists, because if the first species does not exist, imagine C1 is lower than M, then the first species is going to go extinct, and the second species is exactly the dynamics of the first species, right? So it makes sense to think about these species only when they're there. So we're going to say, well, let's put then P1 at the equilibrium, because the equilibrium P1 does not depend on the other species, right? And so we can plug in here this value, and then we can solve for P2. And I'm going to spare you the algebra, but what you get is P2 star, if it exists, should be M over C1 minus C1 over C2. So we want this thing to be greater than 0. So when is this greater than 0? You can write as M over C1 is greater than C1 over C2. Or you can write it as C2, we multiply by C2 divided by M multiplied by C1 is greater than C1 squared over M. Okay, what does this mean? Notice that if C1 is greater than M, so if the first species is there, C1 squared greater over M must be larger than C1. Okay, so what it says is that when the first species is established, it casts some sort of shadow on this axis here, up to C1 squared over M, such that any species C2 that falls in this range of colonization rate will go extinct. Okay, there's no equilibrium, and therefore it has to go extinct. Yes, so like what we need is C2 to be larger than this shadow.
It's like the limiting similarity concept.
Very much the same idea, right? That we cannot be too close to the other species in this space of colonization to be able to survive, right? There is some sort of repulsion. You cannot be too close to C1. You can also see another thing, right? That depending on how much larger C1 is than M, this shadow would be larger or shorter, right? So when I have that C1 is much larger than M, then I'm multiplying this number. This will be, so if this means that C1 is, say, in the middle here, it will cast a very long shadow. If C1 is very, very close to M, it will cast a very small shadow. So like the similarity that you need depends on how different you are from the previous one.
And does this also imply that if there is a maximal colonization rate, then only a finite number of species can coexist?
So that's funny that you say that, because that's exactly what you find in the paper by Tillman that made this model famous. But the answer is no. You can pack infinitely many.
Okay.
And we will see that in a second. All right. So we have then this rule for establishing, right? Like the first rule is C1 greater than M. And the second rule is C2 is greater than C1 squared over M. Okay, now you do the same ordeal for the third species, okay, which I'm going to spare you because I feel generous this morning. And you get C3 is greater than C squared, C2 squared over C1 squared over M. Okay, now you should see a pattern. Do you see a pattern? Here we always have the previous one squared divided by whatever we had before. So if you go up in general, you find exactly the same pattern. So what we can say is that this now would be the shadow that is cast by the second species, right? So the second species is here, C2, and now it casts a shadow that goes up to C2 squared over C1 squared over M. And in general, Each species that is present will cast a shadow, so we can write the expression for the shadow, like we call it L of I is Ci squared divided by L minus 1 of I minus 1, right, from the previous shadow. Okay, so then you can do this recursively. And to close this recursion, you say L of 0 is equal to the mortality rate. Right, so in this case, you say, I take all my colonization rate in order, and then I can check, is the first colonization rate larger than the shadow, which is right now sits at M? If so, I put the species in, and I update my shadow. And then I look at the second colonization rate. Is it larger than the niche shadow that we have currently? If not, it goes extinct, and they take the third. If yes, I put the species in, and I update my shadow, right? And so by doing this thing, we can go through all of these things in just a number of operations that is proportional to the number of species, which means that we can do huge, huge simulations of these things in no time at all. Yes. Yes, it has to be positive.
Species reaches the zero equilibrium.
It's extinct.
Yeah, so, but like the conditions for all of the species are based on the other equilibrium of the previous species, right?
Right. So like the first species, you can see that if it has a colonization rate larger than M,
yeah,
it will always establish. So then you can think, I have a new system, right, that you start having like mortality here. It has mortality where I have right now C1 over M, C1 squared over M.
Right.
Right, and now you have one species, and you do the same game. Right, so it's really like recursive in that way. Right, so, that you can always think of this system with n species, a system with n minus 1 species, but a new mortality, or a system with n minus 2 species with a new mortality, or n minus 3 with a new mortality. Okay, that's why you can go so quickly. Right. So yeah, go ahead then. No, C, we assume that it's positive, right? And then it makes sense to think of CIs only that are larger than M, just because otherwise they will go extinct, right? If you cannot make up your own mortality rate, yeah, you're going to go extinct.
Right, right. I was just thinking if M and C1 are smaller than 1, then it's casting no shadow.
No, they still do, because it's their ratio that matters, right? So it doesn't matter if they're larger than 1 or smaller than 1. It just matters their ratio. Okay? So like you've been knowing me for like about a week. So what am I going to do next? Right? I say, oh, I can do very large simulations. What am I going to do next? Let's see, who knows me? No, not invert the matrix, because I told you that we don't need the inversion anymore. I want to do simulations, and what I'm going to do is do a simulation with what? With random parameter. Thank you very much. Right, so you see that you're getting to know me. And so what we want to do is to draw random parameters, right? So imagine that I say, well, I sample my colonization rate independently from a uniform distribution, for example, that goes between M and M plus 1 uniformly. Okay? So now I have to sample n parameters. So imagine that I sample these n parameters. This is the first parameter that I sample, then I sample this one, 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 etc. n times. So now I have n random numbers. But the model requires me to have ordered numbers, right? So I'm going to take them, imagine that these numbers that I sample are gamma I, right? They are my n random numbers that I got. Then I say C1 is equal to the minimum of gamma I. Okay, so this is going to be the first species, the one with the smallest colonization rate. And then C2, minimum over I. C2 is going to be the minimum over i's such that gamma j is greater than C1 of gamma j, right? And then you go like that. And then Cn will be what? The maximum of these numbers. Okay, so if you work with statistics, these numbers are very useful in statistics, right? I have like temperatures fluctuating. What is expected maximum temperature over 100 years in this place? Or what is the minimum temperature, right? Or what is the maximum amount of rainfall or smallest? So people have derived these kind of numbers, and they're called order statistics. So you can write down the probability distribution function for the minimum number, or for the second minimum number, or for the third minimum number, etc., etc. So the idea is of the algorithm is as follows. We choose a distribution, and we choose a distribution that has support over the positive numbers, because otherwise you cannot have negative colonization rates. And while we're at it, all numbers that are larger than m, which I'm going to accomplish by summing m to all these numbers so that we can forget about m. And then we're going to order all these numbers to get the colonization rates. And then we're going to run this algorithm to see how many species and which species survive. And then we're going to do it for increasingly large systems, right? So, for example, I could choose these entries from a uniform distribution like I've drawn here, or from an exponential distribution plus m, right? So this would be m, and this would be the probability distribution function that I'm using. Okay, that's, for example, another option, or you can choose whatever you want. And then we're going to play this game of saying how many species will coexist once we run through the dynamics, which we don't need to, because we already know like who is going to survive, who's not going to survive without running the dynamics. So here are results of simulations that you find also the code and the results in the folder. And so the simulations are in black, right? So if I start with 5 species, and then I start with 10, 100, 1,000, 2,500. Okay, so if I have 5 species, what is the minimum number of species I can have? It is 1. And it's 1 because the first species by design, because we sample numbers above m, the first species will always be there, right? So the possible outcomes of the simulation are 1, 2, 3, 4, and 5. Okay, and then when I go to the 10 species, it would be between 1 and 10, and then for 100 species, it would be between 100 and between 1 and 100, etc. But you can see here that the range that I'm hitting is not 1 to 2,500, right? Like out of, I think these are 10,000 simulations. I always get numbers that say are about half, right? This would be 1,250 would be the half. Okay, which reminds you of what? Of what we did with the Lotka-Volterra with random parameters, right? Where we had the binomial distribution was the solution. And so for good measure, I'm plotting the binomial distribution on top of these lines. And you can see that for both distributions, asymptotically, right, for n large, these two distributions become closer and closer together. In fact, it's not exactly the binomial distribution, it's the binomial distribution of n minus 1 species, you flip a coin, and 1 you always add, because the first species is always there. Not that it matters when you have 2,500, but just for precision. Okay, you do this with any other distribution, and it looks the same, right? The rate at which it converges to this depends on the distribution, and the side from which it converges depends on the distribution, etc. But this seems to be what we would call a universal result, right? Like that no matter your choice of colonization rate distribution, asymptotically, eventually you're going to converge to the binomial distribution. Which is interesting because it's exactly the same result we got for what? For a model that was also Lotka-Volterra for non-interacting species, and also for a model of random interactions. Right, so now we have 3 different cases: no interactions, random interactions, and hierarchical interaction with a trade-off, giving us the same result. Which tells you that this behavior is not so crazy after all, right? Because the first time you see it, it's like, oh, that's a funny behavior. Maybe it's like very specific to my model. And then, you know, a few years back, I was giving a talk at Princeton about this problem. And there was this guy, Matteo Detto, who's also Italian, who told me, I have another paper with exactly the same behavior. But in this case, it's a model of like tree growing in a forest, where they model all sorts of physiological things, etc., etc. So it's a much more complicated model. What do they get? Exactly the same result. Which then says that this idea that for models with somewhat random parameters, the more species you put in, the more you get out, is somewhat robust, right? So I wanted to do like the derivation of an argument for why this would be the case, and then I wrote it, and I was like, there's no way I can go over this in 20 minutes, which is what we have. And so I just want to give you a sense of how would you go about thinking about this problem for a generic distribution? Yes? Yes. Sorry. The x-axis is the number of surviving species in the model, right? Once I went through all these things, I say you live, you die, you live, you die, etc. So that's this. And this is the probability density function, right? How many times, like the frequency of this result. No, the x-axis is the number of coexisting species, right? So when you start with 5 species, how many species are coexisting? Either 1, 2, 3, 4, or 5. This one is the frequency. So this is fundamentally a histogram. It's just that, like, if I draw a histogram, you would not see anything. So I put just like the lines. So it's the outline of a histogram.
So basically, that means that about half the species for large N, you choose the parameters randomly, about half of them will survive.
Exactly. Exactly. In fact, you can prove, and we're not going to do it right now, that each species is exactly 50% probability of being in the final set, irrespective of their colonization rate. So it's not that the 50% with the lowest colonization rate survive and the other ones die. It's really, if you look at the distribution of the colonization rates before and after, and you plot it like this, it looks the same. So the PDF looks like there's been no process at all. If you look more finely and you compute what is the distance between 2 consecutive colonization rates before and after, you find that the distribution after the dynamics is exactly the distribution of skip 1 before the dynamics. So it's really like they tend to go yes, no, yes, no, yes, no, like that. So this is all in the supplement of the paper. I'm not gonna spend time thinking about that. But I just wanted to show you how would you go about trying to prove something that is somewhat universal. And so what we're going to show, it's only one minuscule result, and we're going to show that the probability of coexistence is exactly of having only one species at the end, so only the first species survives and everybody else dies, is exactly 1/2 to the n minus 1, which is what we would expect under this binomial distribution, when the distribution is uniform between m and m plus 1. And really, like, the thing that I want to show you is just how do we approximate these niche shadows. Like, these are called the shadows that we draw over the axis were called in other papers like the niche shadow, which is a very poetic name. I don't know if it's very clear what it means, but that's the way people call it. And the key is really like to be able to approximate this in the case of large n. And so when you have many species, you can think of what? When I have many species, let's think about the uniform distribution, that it's easier to think about because it's finite support. Then I will have points that are more dense, right? Meaning like the distance between any 2 colonization rates that are consecutive will be smaller when n is large. Okay. Now, here we have 2 processes, right? The farther you are from the previous niche shadow, the larger the shadow you will cast, right? And then the closer you are to the previous niche shadow, the smaller you have, right? So we have 2 competing processes. One is we're packing more and more species into the same place, so it's much more likely that you're falling into somebody else's shadow. But at the same time, all the shadows are shrinking, right? Because you always are just like a little bit off like the shadow of the preceding species. And so it turns out that this result of having 1/2 comes from the fact that these 2 processes cancel each other, right? So that then you have really no preference between one or the other. There's no bias, okay? And so the way we could do like this proof, for example, that it's very difficult to have only one species surviving in this model, is we could write the probability density function for the joint distribution of the first colonization rate, the one that is smallest, the minimum of the numbers that we sampled, and the maximum. Okay? And this you can do for any continuous distribution, right? This has been studied, and it's just like the joint distribution between the minimum and the maximum is just when we sample n numbers, it's just like n times n minus 1. And then this would be the cumulative distribution function that you use, evaluated at the maximum, minus the cumulative distribution evaluated at the minimum, raised to the power of n minus 2, times the probability distribution function at Cn and the probability distribution function at C1. Okay, so this is something that if you look on Wikipedia, you will find this thing. Okay, the problem that we have is that we cannot work directly with these C's, but we have this sort of complicated function with a square. And so like one key intuition is to say, well, we know that our niche shadow is Ci squared over L of I minus 1. Okay, now we're going to define a new quantity, which is by how much are you clearing the previous shadow, right? So imagine that I call Xi is my Ci minus L of I minus 1, right? So here would be this distance, right? Between what is the end of the preceding shadow and yourself. And then if I write this thing now, Li, I can solve this for Ci is going to be the sum between Xi and Li minus 1 is Li minus 1 plus Xi squared divided by Li minus 1. We expand the square and we get Li minus 1 plus 2Xi plus Xi squared over Li minus 1. And so here what we're going to do is do what? We're saying when we have many, many species, Xi is small, and therefore Xi square is 0. We just like neglect this term, okay? And so this is approximately Li minus 1 plus 2Xi, which you can also write as 2Ci, right? Twice the colonization rate minus L of I minus 1. Okay, so this is like the key thing that allows you to do some easy calculation is to just neglect this term. If you don't want to do that, then calculation becomes very, very difficult. So this is exactly our argument is when you have many, 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 many colonization rates, think about the uniform distribution because it's easy. Now I pack 10,000 species between 0 and 1. What is the distance between one species that survives and its shadow? It's very, very small, right? While when I have few species, it can be substantial. But in the limit of large N, this thing should go to 0 quite fast and surely faster than this, right? And we only want to prove the case of N goes to infinity because we know that at the beginning, this distribution all give you marginally different numbers. Okay, so this is here. Now, to do the actual calculation, it's a bit annoying that you have to take care of one thing only. And the first is, imagine that we want only the first species to survive. We really have two cases that we need to treat separately. The first case is the niche shadow of the first species extend to a certain extent, and then all the other species fall into this shadow, right? So let me just draw it for you, that then it's easier to understand what I mean by this. So case one is we have here is my M, and the maximum is N plus 1. And now we have, I don't know, C1 is here, and it casts a shadow. And now we say all the other colonization rates that we sample, which are N minus 1, they all fall inside here. All of that, right? So this is one part of the equation. The other equation is when I have C1 that is big enough, and then here I have M plus 1, then the shadow of C1 could extend beyond the range, right? And so it doesn't matter what the other numbers are, they all would be extinct, no matter what. But so it turns out that for this, you do one integral for this and one integral for that. These are two mutually exclusive cases, so you can sum the two integrals. Okay? So let's see, under this condition, right? So we want to say, what is the maximum CI that I can have such that we're in case A, right? We need 2 times CI minus L1 to be smaller than M plus 1. Okay, so you solve these integral and you can see that like this holds when C1, sorry, it's between M and M plus 1/2, of course, right? So if it's in the first half of the equation, in this case, it's when CI is C1 is greater than M plus 1/2. Okay, so then we take this equation and then we integrate for C1 and Cn, plugging in the densities of this distribution. So for a uniform distribution, the probability density function is just a constant 1. So that's easy. And then what would be, this would just be like, let's write it as, for here, phi of z would be just what? Z minus m, right? Because we started at m, right? So these would go like, we have m, and then it starts going up, right? These would be phi of c, right? And this is m plus 1, this is 1, and this is m. Okay, so it's going to be just this line, but then shifted by m. Okay, so here we can write z minus m. Now that we have all these pieces, we can just plug in these density. So because of this fact, right, then it's very easy to plug it in here because we have Cn minus m minus C1 minus m. So then we get f of C1 Cn is just n times n minus 1. And then here we're going to get just Cn minus C1 raised to the power of n minus 2. And then that's it, right? Because these are constants. So these things that look a little difficult, it turns out to be just these. And so the first integral that we can do is to integrate these. Of course, we have a double integral. The first one is like the value for C1 that goes between m and m plus 1. No, this is not the integral only of the left-hand side. Let me write the integrals here. So here go between m and m plus 1/2. This is the value of the minimum. And then the maximum can only be exceeding C1, right? So it goes between C1 and 2C1 minus m, which is the value of the niche shadow, right? So we need the maximum to be within the shadow of the first species, such that it means that all of the values will fall into the shadow of the first species. Does the logic of this make sense? Yes.
Joint distribution just to prove that C1 and 1, C1 and Cn exists with the other species outside.
Because Cn is the maximum. So if the maximum falls within the shadow of the first species, then all of them must fall into the so we just need the maximum. That's why this is a simpler calculation. So you can do this if you feel like doing integrals, or you can trust me, and this is like to the negative n. Okay? And then we have to do the other case, in which we have the case in which C1 exceeds Cn, but then this, I think I have a typo here. I'm not sure I have the right integral here, because this seems different from what I had in mind. But anyway, the limit for integration is surely like between m plus 1/2 to m plus 1. And then the other one has to go between C1 and m plus 1. But I thought we needed just to integrate C1. So maybe this one, let me check and then get back to you because I didn't, I don't know what am I trying to do here. But I remember that the answer is correct, is 2 to the negative n. So if we sum these things, we will get 2 to the n minus 1. This is the probability that the number of coexisting species is equal to 1. Sorry about that. All right. And so this is consistent with our claim that this would follow the binomial distribution. And the way you prove like the full binomial distribution is to say, exactly as I did here, like I computed the probability the first species kills all of the rest. You can say, what is the probability the first species kills 3, or kills 2, or kills 1? And you get like similar looking integrals. And then you can sum them according to the number of combinations that you can have of each one of them, and then you can recover your distribution. Here it's above the shadow of C1, while here it can go all the way up to m plus 1. Because we're in the case of this one exceeds, the shadow exceeds this. It's just that I'm not sure that I had here the right function. Probably I did, but I would like to double check it. Doesn't matter, like you can read it in the supplement. This was just to give you a sense of this approximation is really what matters. All right, so before we conclude, because we have 5 minutes, I wanted to say, just like go through some of the papers. So the original metapopulation model is the paper by Levins. And then this model that we've studied has a very long history. And in fact, like some of the best theoreticians in ecology studied it. It was proposed first by Alan Hastings in 1980 in this paper in Theoretical Population Biology, where he derived this model by just extending Levins, and then noted that better competitors needed to be poor colonizers in order to coexist, right? Which makes a lot of intuitive sense, and he formalized that. Then this model is sometimes called the Tillman model, competition colonization model by Tillman, because of this paper in 1994, where he did a very thorough analysis of the model. He noticed this idea of like, we can compute the equilibria in this way. And then he has this quote that was exactly like the point of like, can we have infinitely many over a finite support? And he could coexist, right? But then he had this idea of limiting similarity, exactly like the questions that you had. One foray into other great theoreticians that derive the same model in a completely different context. Martin Novak and Bob May derived exactly the same model in the context of infections. As we were saying at the beginning of the class, right, there's this parallel between metapopulation and disease models. And so they were thinking of like different bugs that could infect people and kick each other out. And they were showing that these things would not lead to a super bug that would kill everybody, but rather they would get frozen in these kind of states. So this would be, in this case, like colonization would be virulent. And then like this incredible lineup that includes also Simon Levine, Jonathan Duscio, Steve Pacala studied the model again. And they studied actually in this limit that we've been thinking about, in the high diversity limit. And they highlighted some pathological behaviors of the model, which I agree with. And then they packed infinitely many species into a finite space, but they had a construction, right? Like, so you had to choose exactly this number precisely. And if you change any of these numbers, it will burst into flames. And then you would go back to a much fewer number of species, right? So it's some sort of fractal choice of colonization rates. While what I just show you is you want to pack as many as you want, just start with twice as many and you'll be fine, right? So that it doesn't really need like a lot of fine tuning. And then the paper that I presented is this by Zach Miller and Maxime Clenet. And there's a funny story that I was talking with Maxime. Maxime was looking for postdocs. He was a grad student in France, like working with a mathematician, Najim. And so we Zoomed, as you do. And then he was telling me about his projects for his thesis. And so he tells me about the first project. I'm like, oh, that's interesting. He tells me about the second project. Then that's very interesting. And then he says, And then I studied the Tillman model with many, many species and random colonization rate. And I told him, and now you're going to tell me about the binomial distribution? He was like, wait, what? Right? So it turns out that my group and his group had studied exactly the same model, which, mind you, was like from 1997. So after 30 years in which nobody did this work, two groups were doing exactly the same work exactly at the same time. So then Maxime was like a little taken aback and I said, let me talk to your professor, like to Francois Massol, and we'll figure it out. So then I contacted Francois and said, why don't we join forces? What sense does it make to write two papers saying about the same thing? And so then we had this collaboration. And it's just funny because it basically never happened to me in 22 years. I think there's another case in which I went very close to somebody else's work, because I tend to work on problems that are at least 30 years old, right? They have to be well aged, like balsamic vinegar kind of problems, right? I don't work on the new, like fancy thing that people are interested in today. And so it almost never happens that somebody else is working and doing exactly the same thing that you're doing. Anyway, it's a fun paper to read. And this brings like my lectures to a close. So I just wanted to show you like that even though the Lotka-Volterra model is 100 years old, there's still a lot of things that you can do with it that no one has done. And there's in fact like a great deal of mysteries surrounding exactly what's going to happen. And yesterday at dinner, we were having discussion on the type of dynamics and things like that. At least in the large species, number of species limit, I think it's still fun to play with this model after 100 years. So thank you for a fantastic class. Like I'm so excited to see people excited about this type of problems and coming and asking questions and saying, I'm trying to do the derivation again and I got stuck here. It's really like warms my heart to see that there are people that are so committed to science and young people that are going to make this field better. So thank you. Mm-hmm.
So let's say you have, n species. And you've got, whatever, n by 2 or close by number of species that survived, and you have them sitting there. Now you want to add another species to this, which comes in with its own CI.
Mm-hmm.
What's the probability that it'll get through? It's not half, right?
So it's not half. And so what you can do, well, there are a few things that I didn't say because I didn't have time. One thing is, in this model, because of this feature, putting all the species together, or if you have a pool of species, putting one at a time, you end up in the same exact place, right? So it doesn't matter whether you put all the species together or you have invasion one species at a time. Now you can think of a slightly different approach, which is in fact what Bob May and Martin Novak were doing, which is I take every time a new species and then I stick it into the system. Do I saturate or do I keep growing, right? So what happens is you keep growing for forever, but the growth is fundamentally logarithmic. So it's quite fast at the beginning, and then it becomes more and more difficult. So it still is a positive contribution. So each species that you add sends on average less than one species extinct, but and there's no saturation, but then it's very, very small growth after that. Yeah, so theoretically you can really have infinitely many species just by picking different numbers and sticking into the system. If you're willing to wait exponentially long time, you can get as many species as you want. Yeah, what is the biological context? Like it says just that if you are barely clearing your mortality rate, then you're occupied very few patches. And also, you're not going to be able to outcompete a wide range of competitive abilities, right? Because you're just like barely making it yourself, right? You're just clearing this thing very slightly, so you're not going to do a lot of damage. While if you are thriving, right, so then you're very far from the boundary on the left, then you can really like outcompete a much larger variety of species. Don't you want coffee? I want coffee. And I'm around until Sunday. So if you have other questions, just ask me. All right? Thanks.